Hi guys, how's it going? So today actually we're looking at combination sum 4. So if you have already done combination sum 1 up to 3, you realize that this question is actually different from the previous one. So let's just read through it and you'll see how different it is. So you're given an array of distinct integer nums and a target integer target. Return the number of possible combination that add up to target, right? So essentially, you can think of it as like you're given this nums, and you need to find the numbers that actually sum up to target. And unlike with the previous one, whereby we didn't have the privilege at some point to reuse the numbers, in this case, looking at this example, you can reuse the numbers as many as you want, right? 1, you can reuse it 4 times so that you can actually get 4. You can add 2 and 1 to get 4. That's still okay. So you can do something like that, right? And the second most important thing that you can realize from this question is that we are told that note that the different sequences are counted as different combination, meaning that you can as well do something like 3. You can take 3 and 1. This will still count, and you can also take 1 and 3, right? If you know if you did the previous question, you'll realize that this was actually considered as a duplicate. It was not allowed to do something like this, right? So how would you then go about something like this? So one way we can brute force this, or maybe let me say backtrack. By backtrack, I mean we can take let's see, in the example we're given 4. Okay, we're given 4 and we're given 1 2 3. So we can take the target and we can subtract from the target up to the point where we get 0. For instance, we can do something like this. We can subtract 1, right? And we can subtract 2, and we can subtract 3. So these numbers are the numbers that we've been given inside the list. So these are the numbers, right? So the reason we're subtracting this is because we want to find the numbers that actually sum up to 4. So when we subtract this, we actually get 3, okay? We actually get 2, okay? We actually get 1, okay? So now we can take, we can continue from this and say we can do the same thing and say subtract 1, because they want us to reuse these numbers so hence I'm reusing 1. So here I'm just gonna say 2 and 3. So we're just gonna subtract this. It's gonna give us 2. This is gonna give us let's see, actually this is supposed to be like this. Then this is gonna give us 1. Then this is gonna give us 0, right? So what does this mean? It means that this path here, it actually sum up to 4, right? It actually sum up to 4. This is the correct, so, and it makes sense because if we take 1, right? If we take 1 and we take 3, they sum up to 4 because we managed to get to 0. So this also should signal you something. It should signal you that if it happens that total is equals to 0, then that means we are able to sum up. So we should return 1, right? Because here we are told that we should return the number of possible, so the number of possible, not necessarily the list, but the number of possible combinations. So hence here we have to return 1. Okay, so let's continue with the other ones. So let's say we subtract 1, that's return 1, that's fine. We subtracted 1 from 3, it returns 1, that's fine. But then what happened when we subtract 3? We're gonna get a negative 1. Okay, so when we get negative 1, it simply means that this path cannot sum. Let me just use a different pen. This path here cannot sum up to the root, cannot sum to 4. So which means that we have to return 0, so it does not count. So if total is less than 0, we just need to make sure that we return 0. Okay, but this solution that we have here, it's gonna be exponential. So how can we therefore reduce the time complexity? So if we can look at this, problem where we have 3, for example, here we have 3, we know how many results we're gonna get from 3, right? So how about then if we get like 4 minus 3, we get 1. Maybe we can have a similar situation where we have 3, right? So how about then we cache all of the results. Where we get to 3, we cache all of their results. So this is also called memoization, for those who don't know. So we cache the results so that we don't have to do the same computation. So this actually is going to save us, it's going to reduce our time complexity from m times n. Okay, so this is not bad at all. Okay, so this is what we're gonna do. I know that I might have confused you maybe, but I'll try to explain it more in depth as we're writing the code. So I'm just gonna share the code now. So what we're gonna do is that we're gonna create this function. We're gonna call it backtrack recursion, and from this we're gonna take in the target, we're gonna take in the nums, and I'm not gonna write the memoization code now, I'm gonna write it later. I just want you to understand the core of this problem for now. So like we said that if it happens that the target, okay, if it happens that the target equals to 0, then we just wanna return 1, because it means that we can sum to the target. Okay, however, if it happens that the target it's actually less than 0, then we just want to return 0, so this does not count at all. So because that path, meaning that path cannot actually sum to the target. Okay, so what we want to do is that we want to reuse all of the numbers, because we are told here that the number, we can use it as many times as we want, right? So that's what we want to do. We want to reuse that number. So I'm just going to say for n in nums, so this is going to give me all the values in nums, because I want to reuse them. Then what I want to do is that I'm going to say remainder, because just like in the diagram, I showed you that we're gonna take the target, then we subtract it, right? We subtract it by n. So the reason we're subtracting it is because we wanted to possibly get to 0. For if it give us a negative, then we know that we can't sum up to that number. So what we're gonna do is that we're gonna call the backtrack function, and we're gonna take the remainder as our new total, and we're gonna pass the nums. But we're also gonna say results, because we want to return the results equals to 0. Then we're gonna say results plus equals to the results that we're gonna get from this backtrack. Okay, so you can think of this backtrack at some point. It's gonna return 1 as it reached the bottom, or it's gonna return 0. Then we're just gonna add plus results. We're just gonna add it to the plus results. So if it returns 1, that's a +1 for us. That means that path was able to sum up to the target. If it returns 0, that path was not able to sum up to the target, so we just don't want it. Okay, so that's that. So what we're gonna do, guys, is that we're just gonna have to return the results. Okay, then what I'm gonna do is that I'm gonna say return backtrack, and I'm gonna give it the target, and I'm gonna give it the nums. So these parameters are coming from here, and I'm calling it inside here. So I'm just gonna run this. Okay, it seems like it's working, so I'm gonna submit. It's taking a while. That is because now it's running, the time complexity of this code is exponential. So we so you see the time limit exceeded. So we are essentially computing every possible combination from scratch. So, but even if we know that we did that already, so we need to introduce another technique called memoization, right? So memoization, you can think of like, if we computed a specific combination, we don't have to do it anymore. So I'm just gonna say memoization equals to hash. Actually, I'm just gonna pass it as a, okay. So what I'm gonna do here is that I'm gonna say memo, you pass it here, then what you do is that you cache every result. So for instance, you're gonna say, actually let's do this. So you're gonna say memo and target equals to 1. I'm just gonna copy this again. On every return statement, I just want to cache the results. So here, just gonna do the same thing. Just gonna say memo results. Then what happens is that if it happens that if target in memo, then we want to return memo target. Okay, so I'm gonna check, hope I did not make any silly mistakes. Okay, I did, which was to miss the memo here. Okay, okay, let's submit now. So it should be fast because the time complexity is off, and then it was. So yeah, that's the solution, guys. Essentially, I hope you guys actually enjoyed this. If there's anything you want to add, you can add it into the comment section. Thanks, guys. Bye.